Hi all, welcome back to Environmental Science. Um, Today's lecture, we're going to discuss kind of components that go into deciphering or deciding or influencing the growth of a population, or how dense a population is in a given region. And really, we often break these down into kind of two categories. Although the categories with the involvement of humans in on this planet, I guess you could probably say the categories are getting a little more fuzzy, or a little less clear. So, looking at it, so there are two main factors again that regulate this. And so one factor we call density independent effects. That means the density of the population, so how many individuals you can get in a given region, okay, is independent of, or the factors that determine this are independent of how many individuals are there. Okay? And so these are normally what we call natural disasters, or kind of natural systems. So freak weather events like wildfires or tornadoes or hurricanes, volcanoes, these things have all been labeled as density independent effects. It doesn't matter if there's 1,000 people next to on the coast of Florida when a hurricane hits, or 10 million people. The hurricane's still going to hit that region. Now, that being said, there is quite a bit of evidence that suggests that some of these once thought of density independent effects might actually be linked to density dependent effects. And here's an example. So normally, like all natural disasters kind of get lumped into this density independent effect. But like if you think of things like wildfires, okay, and the severity of a wildfire, it actually can be related in many cases to the density of human populations in the region. And here's why. Okay? So as humans occupy a region, especially arid regions, they take water out of that environment. Okay? And if the humans are taking water out of that environment, the landscape is becoming more dry. Okay? And if the landscape is becoming more dry, it's potential for wildfires to happen more often. So that's just like a simplistic example where population size could actually have an effect on some kind of natural weather effect. Same thing with some of these natural weather effects like tornadoes. We've seen that tornadoes happen typically when you have temperature differences between between the land and the air that are drastic, okay, which can create a vortex, and we have these vortex kind of that often occur next to kind of cliffs and things like that, where you have water and a cliff, and the cliff is really warm and the water is really cool. You'll get these thermals, which are these vortexes. The winds will start to kind of circle up, and so the air starts to rotate. And if you've ever been in a canyon and you can watch birds ride the thermals, or they ride these vortexes, and so the birds will circle, okay, and they'll ride one warm pocket to another, and they won't actually have to do much because the air is rising, so it brings them up, so they won't have to flap their wings very often. Well, what we've seen is regions where maybe we have what we call an asphalt desert. So you have big cities in open regions with lots of blacktop or asphalt. They tend to heat up a little bit more. we've seen quite a few scientific studies that suggest these regions where we have lots of buildings that reflect sunlight or absorb sunlight, a lot of parking lots, roadways that are really congested in certain regions. Okay, they absorb a lot of the heat, and then that heat, it's like a hot spot. Okay, in the region, and what we've seen is actually in those regions they can actually influence wind patterns. They can influence the potential for tornadoes to develop during certain weather effects. And so, long story shortened, sometimes population size can alter some weather effects and geological events. And global climate change has definitely increased the number of hurricanes, severity of hurricanes, number of tornadoes, severity of them, number of wildfires. So in the grand scheme of things, if humans are related to climate change, and our population, given how big it is, and our use of fossil fuels and other things, is actually having an effect on these density independent factors. Okay? But normally when we think about this, these are not related to the population size, but these are. Okay? These are directly related to how big the population is, or the size of the population, the density of the population. And normally that is, the more dense the population is, the stronger the effect will be. So effects like competition, maybe that's competition for food, or maybe it's competition for nesting sites, maybe it's competition for establishment on a hard surface, maybe it's competition for all kinds of things. The other big one that we often see that's a density dependent effect is diseases and parasites. So the more packed, or the higher the population is for a given region, the more likely you are to see the transfer of viruses and bacteria and parasites within that population. Okay? Those are density dependent effects. So here's just a quick example of one that's fairly well documented. So if you take something like a chipping sparrow, or a savanna sparrow, or really any sparrows that will often nest in a given region with lots of females nesting kind of in the same region. If you have just a few breeding females, the number of surviving young is significantly higher than if you have lots of breeding females. So when we're talking about, a few, like 1 to 10, maybe even 1 to 30, the number of surviving offspring on average is around 4. So the bird will lay typically 4 eggs, and all the eggs will survive. All the offspring will survive. Okay? As you increase the number of females in a given region that are laying, and they're competing for nest sites, they're competing for food resources, they're competing, and they're having competition, they're competing for mates, they're competing for all kinds of things in this given region, that changes how many offspring can survive. So when we're talking about 60, 70 birds in a given region, maybe they're producing 1 offspring. Okay? And so that can change your population a great deal. If you're only producing a single offspring when there's lots of you around, it's, you're kind of reaching that carrying capacity. The carrying capacity of the population from a nesting effect, okay, might be somewhere around the 70, 80, because anything less than 1 offspring per individual is, you're not reproducing, and so your population is not growing. Maybe down here where you have very few nesting in the given region, 4, if the female, because most of the most of the song sparrows or sparrows are laying somewhere around 4 eggs. If they're hatching and reproducing, about every single egg is surviving, then you can see that's like exponential growth. So kind of keep these things in mind, that you can get competition between individuals. You can get competition for food resources, where every one of these birds is, all these females are going out and getting seeds or insects to feed their young, and when there's less seeds and insects, they have to spend more time away from the nest, more energy getting food resources, and they're getting less food resources, so they can't raise all their young. So some of the young die, and the population doesn't increase as fast because of the competition, and because you're batting up against, you're getting close to that carrying capacity for that given region. Okay? Those are density dependent effects. Okay? It depends on how many individuals are in the population or in the region. Okay, so there's other things that can often alter or change the population, and humans, of course, were one of them. And because we know how populations grow, and because we know that half of the carrying capacity, okay, so if you know what the K is, half of that, as long as this is a logistic sigmoidal growth, okay, half of that is the highest point of growth. Okay? So half the K is what we call the maximum sustainable yield. Okay, and for commercial fisheries, for marine habitats, for sure, this is often the point of harvest. Okay? The same thing with freshwater fisheries, and really actually in many cases other things that we might exploit wild organisms for. If we're exploiting a wild organism, we're not controlling their population by breeding them in pens. Excuse me. The premise is we can sustain our harvest for years and years and years and years if we sample them at the maximum sustainable yield. So let's look at that. So if this carrying capacity, let's say it's 1,000 individuals for this population. Okay? So there's 1,000 individuals, carrying capacity would be here at 1,000. If we take half of that, this is the highest growth rate in this sigmoidal growth curve. This is the highest growth rate. So that means if you keep your population, if you sample your population, and you only take the number of individuals above the maximum sustainable yield, okay, so maybe you're taking 200 individuals if carrying capacity is 1,000. Maybe you're taking 200 individuals every season from this small population. You're taking 200 individuals, that pushes it back to the maximum sustainable yield. Then that's the highest growth rate, and it will return the highest amount of individuals. Now, remember, this fluctuates over time, so it's not stagnant. But if you know what your maximum sustainable yield is, or close to it, okay, then you can harvest back to the maximum sustainable yield, and that gives you the biggest bang for your buck. And that's what a lot of commercial fisheries are after. Okay? In fact, they actually harvest just below the maximum sustainable yield, because other things can happen in the environment that are unpredictable, like disease outbreaks, okay, low food resources, potentially, in a commercial fishery situation where you might have big events of like red tide or something that is not expected, or you can't predict what's going on. If you harvest just below the maximum sustainable yield, it takes into account some of those unknowns. Okay, but you can still harvest at the maximum sustainable yield. It just depends on the managers of that commercial fishery. But that's where they're typically sampling, and they're trying to knock it back to the maximum sustainable yield, so they get the biggest growth rate for the next generation, for the next season. And then they take that growth rate, however much the population grew, and knock it back down. However much the population grew again, and knock it back down. And that's what they take. Then you can maintain a steady, constant population that's reproducing at its highest efficiency, and that is when a commercial fishery works, is when things like that occur. They don't always work that way, which we'll come back and talk about later on when we talk about some more commercial fishery stuff. All right, life history adaptations is really from an evolutionary perspective. Okay, so certain organisms, certain species have characteristics in which they kind of adapt to different environmental conditions. So one way that we kind of lump organisms into are kind of these two different categories. We call them either R-selected species or K-selected species. So they either have an R-selected adaptation, which means they grow really fast and they don't live very long. Right? So they take advantage of resources when they're available. They grow extremely fast. They reproduce really fast, and they don't last very long. Like their lifespans aren't very long. So lots of invertebrates, rodents, small fish species, lots of marine organisms that have really fast reproduction cycles will be considered R-selected adaptations. So your sponges, sometimes your sea stars, your sea urchins, these kind of things, they can grow really, really fast. They can live in unpredictable environments, so the environment doesn't have to be stable because they can have these boom-bust kind of cycles and still live. And then you have what we call the K-selected species. These are normally the species that are long-lived. It takes a long time for them to develop young or to reach maturation, and they normally are sitting close to carrying capacity. Okay, so their population sits around carrying capacity. Maybe it rises above it a little bit just to crash down a little bit and then back and back, but they're not the boom-bust species like R-selected adaptations. R-selected, they'll have exponential growth, reach the carrying capacity, crash, go for a little while, exponential growth, reach carrying capacity, crash. R-selected are not that way. Okay? And so R-selected species typically have very long lifespans, and maturation time again is long because they live for a long time and sit at that carrying capacity for a while. Now, of course, there are species that fit in between these, that don't fit either one of these very well. Sometimes it depends on the environment. Sometimes organisms will be R-selected in one environment and K-selected in another environment. But this is just a way that we can categorize different species. Okay? So again, just some kind of adaptations that you might expect for an R-selected population. Okay? Early age at first reproduction versus K would be late. Homeostatic capabilities might be limited, so they might have a limited capacity to withstand different environmental conditions, so they might die off really quick, or they might not be able to delay maturation or delay production of eggs or anything like that, so they might lay lots of offspring in not a very good environment, and most of those offspring die. And versus a K species will typically lay very few or have very few offspring, but most of them live. Okay, and so mortality rate often in R-selected populations is very high. K is very low. Right, parental care in R-selected, none. K, often there's some, if not extensive. Size of the eggs or the number of eggs, R normally produces lots of little individuals, or lots of little babies, and then K typically a couple, a few. Okay? This is an example of exponential growth. Okay, so these are roaches. So if you have, hopefully you've never seen something like this in your home or someone else's home, but you can have exponential growth, explosion of things like roaches or locusts or other organisms that can produce lots of offspring in a short period of time, can have an explosion. But what happens when all the food's gone? It's a crash. Okay, so the consequences of an exponential growth is huge production, really quick. K is reached, overshot the K typically, and then the population crashes. Normally it doesn't go extinct, it crashes down to a manageable number until a new food resource or a new resource is established, and then they can explode again. Okay? All right, when we come back, we'll talk about population demography, which is really breaking things up into different groups like age cohorts and size cohorts potentially, and these kind of things, which is important for environmental science to see. Hey, especially in maybe marine systems where we might be interested in fishing a certain size of fish. Okay, if we know how many individuals are in those size cohorts or age cohorts, then we can set limits around those and see what the effects from humans fishing on those size components could be. Okay, next time we'll come back and talk about population demography.